So we have finished about the convective heat transfer, all these momentum boundary layers and thermal boundary layers, and we learn about how to make use of them to calculate the useful quantity, which is the heat transfer coefficient in Newton's law of cooling. We actually saw that there is an analogy between the momentum transport and heat transport, and we have seen that the key quantity in the Nusselt number can be estimated using the Reynolds number and Prandtl number, using the flow conditions, which corresponds to the Reynolds number, and the fluid properties, which corresponds to the Prandtl number. And we have actually talked about different cases where the boundary layer thickness for the momentum and the temperature are actually different than each other or similar to each other. So that's all about our convective heat transfer. Now, I would like to, before we start learning about the mass transfer, I would like to talk about some applications, and particularly and very important application of heat transfer in the industry, which is called the heat exchanger design. So we are going to talk about a very important topic called heat exchanger design and analysis in this class, in this lecture, as well as I guess maybe tomorrow we can continue that. So this is going to be lecture 13, but let me call it lecture 13.2. Lecture 13.2. Heat exchangers. Okay. Say page 1. Okay, so let's write heat exchanger design and analysis. A very important topic you should learn, you should know as chemical engineers. And let me write down a paragraph. So far, we have looked at solid-solid, and solid-fluid heat transfer. Now, let us look at a very important practical problem. Which is fluid-fluid heat transfer. So we want to heat a cold fluid using a hot fluid, or cool down a hot fluid using a cold fluid. Okay. The equipment in which fluid-fluid heat transfer is carried carried out is called a heat exchanger. Probably you have seen this name in your what is the name of the course? I think Introduction to Chemical Engineering, where you learn about balances, right? And equipment of equipments in the chemical plants. Yes, right. Okay, and it's very common in chemical processes. So they can come in two types. Can be of two types. Either of the two types. Depending on how they contact, depending on how the fluid contacts with the other fluid, they can be either direct heat exchangers or indirect heat exchangers. And the direct heat exchangers involves direct contact between two fluids. For instance, cooling towers is one example. In cooling towers, maybe you know about them, you have like a falling film, either a falling film or water dropping down through like meshes so that they separate from each other. The water goes in, down, water falls down, and then the air is flowing in the opposite direction. And then it directly contacts the water. There is no other surface in between them. So cooling tower is a good example of direct heat exchangers. Okay. They can also be indirect heat exchangers. And this involves indirect contact. So you should have another thing in between the two fluids. Between two fluids. Separated by a solid phase. Okay. Mostly you see the heat exchangers in this type. So the vast majority of heat exchangers in industry is of this type. And this is the one we would like to talk about in this course. Okay, so we set the stage. Now let's talk about other classifications. You can classify the heat exchangers depending on the arrangement or the architecture. Okay, types of heat exchanger based on architecture. So one of the common ones used in the industry are called double pipe heat exchangers. And so basically, let's say type of indirect. Okay. Double pipe heat exchanger. And they can be either co-current or counter-current. Okay. We'll talk about them. Second type is shell and tube. Heat exchangers. And the third type is compact heat exchangers. So let's say, let me briefly show you double pipe heat exchanger. You basically have like two pipes. This is one pipe. This is another pipe, basically. So you have two layers separated from each other. For example, you have the hot fluid in this region, and you have the cold fluid here. Flowing, both of them are flowing, but depending on which way they actually flow with respect to each other, they can be co-current or counter-current. You basically have two pipes, one inside the other. The shell and tube actually looks like this. You have a tube. It goes back and forth like this. So many times, not necessarily 3 or 2 times, but it's inside like a bigger shell. But then you can actually send the fluid one, for example, the cold one, and then you can send the hot one here. Okay, so these are the tubes. You can have many of them, and this is the shell. Okay, you can come like generally they have this sort of architecture, the shell and tube ones. You have this shell side here, and it basically opens to many channels here. Sometimes they have this arrangement. They don't go back and forth, but so you can have the hot fluid in, and you collect them here. And then this is the shell side. So you actually send, and it goes around the tubes. Okay. So that you can have this arrangement either. So generally you see them in this arrangement. You basically collect all at one side. You pump them along the tubes, and the tubes are actually inserted in the shell, and the shell contains a different fluid. Okay. The compact heat exchangers, they have actually large heating and cooling service requirements. With a small size. The key is the high heat transfer surface area. Surface area. Okay. Per unit volume. Per unit volume. Or, in other words, surface area density, you can call it. Okay. One example is the human lung, right? Human lung is an example of a compact heat exchangers. Okay. You can have plate type heat exchangers. You can actually put it under the compact heat exchanger category. Plate type heat exchangers, etc. So let's focus on the shell and tube heat exchangers. Okay, so it's basically what we're going to see can be applicable to double pipe heat exchangers as well, just because we're going to focus on one tube, the flow, like fluid flowing in one tube surrounded by some other fluid. Okay, so the tube, like fluid is flowing around the tube, inside a tube, and the tube is actually immersed in another stream. Okay, so let's say design of heat exchangers for the shell and tube. Heat exchangers. The idea is similar to the double pipe. Also applicable to double pipe heat exchangers. So our model is going to have something like this. So we have a tube, right? You enter the, you push the hot stream in. You get the hot stream out. Hot out. Right? And you have the cold. Or maybe let's do the cold here. So. You can send the cold in here and the cold out here. This looks like basically like a double pipe heat exchanger, but you can actually use the same model to like make like many tubes here, and then it's going to apply to the shell and tube as well. So it doesn't matter for the sake of simplicity. They would give us like similar mathematics, right? And since you have the hot stream entering from the same side as in the cold stream, this is called concurrent flow. Concurrent arrangement. And the you can also alternatively have the same setup, but you can send in the cold from here instead of the other way around. But not changing the hot, for example. This is called counter current arrangement. Okay. So let's have a look at first. Let's get a physical intuition about what's happening here. Let's have a look at the temperature which is changing along the streamlines, right? So one can actually plot the temperature as a function of position. For example, the temperature here versus temperature here, 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 here. So how does it change as the hot stream actually flows? Similarly for the cold, what is the temperature here, 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 right? So you can actually make like pick some slice and see what is the temperature here for the hot, what is the temperature here for the cold, right? At different positions. So one can actually plot the temperature as a function of position. So let's say the temperature is increasing in this direction, and then the length is increasing in this direction. And let's say this is the end of the exchanger. And imagine that the hot stream is at this temperature, let's call it TH1, T hot 1. And this is, imagine that it's cooling down like this. And let's say this is T hot 2. And the cold one, let's make it blue. Imagine that the inlet cold temperature is TC1. And it's going to cool down, cool down, cool down, like this, right? Is this possible?
No.
No, it's not possible, because you should have the cold stream cooled down below the hot. So the theoretical maximum is going to be the hot temperature. It cannot be larger than the hot, otherwise the heat is not going to transfer anymore. This is T cold 2. This is the concurrent arrangement. Okay. Let's write it particularly concurrent. And we say that TH2, the hot out, is larger than T cold out always for this arrangement. Because there has to be heat transfer. From the hot fluid to the cold one. And what happens is, as you can see, this actually curve actually this curve gets less and less steep, right? Correct. So this is because of the following effect. As the temperature difference between the shell side and the tube side decreases, so does the heat transfer rate. So rate of change of temperature gets smaller and smaller each time because the difference gets smaller, right? And you can argue that for an infinitely long or infinitely large heat exchanger, for an infinitely long heat exchanger, what happens is that T hat 2 almost equals to T equal to. Okay, they can actually get equal to each other after, like asymptotically they approach to each other. But it's asymptotically. It's not a finite amount of length that they become equal temperature. Okay. Good. How about the countercurrent arrangement? So you get you're going to have a different plot this time because the arrangement is different, right? And imagine that we start with the same hot in and cold in. Okay. Imagine that this is your T hot 1. Okay. It's going to cool down because of the cold fluid, right? Like this. But now, surprisingly here, for the cold temperature, if this is T cold 1, like the same as in this one, so this, let's call it T cold 1. If it enters from the other side, it's going to increase, 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 and it can even be larger than the outgoing hot temperature, but not larger than the incoming hot temperature. It can never be. This is the theoretical maximum for a cold stream to be at. So, but surprisingly, it can exceed the T cold 1. So T cold 2 can exceed the T hot 2, right? But again, T hot 1 is larger than T cold 2 always, right? We say that T hot 1 is larger than T cold 2. This is T cold 2 always. But TC2, the outgoing cold temperature, can be less than or greater than or equal to TH2, right? So these two can actually compare in many ways. So either of them might be larger than the other. Okay. Unlike in co-current case. Unlike the co-current case. Yeah. Okay. Any questions so far? Okay, so let's move on for maybe 10 more minutes if you are okay with that. Okay, so let's see a couple of like special cases to get more intuition about what's going on. Okay, let's get more intuition. One case you can come up with is you can actually boil something or you can condensate something. For instance, if there is condensation, hot fluid does not change temperature, or hot fluid temperature does not change. Right? Because the condensation happens at a constant temperature for most of the substances, at least for pure substances, I would say. So the hot fluid temperature is going to be at a constant temperature. Let me do a better job. This is T hot 1. This is T hot 2. And the cold one is going to heat up. But the rate of change is going to decrease with time, or with the length, because the difference gets smaller, the heat transfer rate gets smaller, right? This is a pretty good amount of intuition, I guess, about what we should expect from our equations that we are going to derive. And let's write that this is a constant temperature, right? So it's more like a substance that doesn't change its temperature at all, or maybe approximately does not change its temperature. Like maybe the amount of material is large. Maybe it's not condensating, but you can see the similar situation when the flow rate of the hot fluid is very, very, very large, so that the temperature change is not appreciable. Or maybe its heat transfer, maybe its heat capacity is very large, so that you need to transfer a lot of heat to just change its temperature very slightly. So this can be expressed, the situation can be expressed as Cp hot is very, very large, going to infinity, right? The specific heat capacity is Cp. Another thing, as the opposite of this, if there is boiling instead of condensation, if there is boiling, this time cold fluid temperature does not change. And this should look as follows. This is T equals 1. Goes like this. This is T equal 2. And the hot side is going to change its temperature, asymptotically reach Tc2. So this is T hot 1. This is T hot 2. And the arrows can actually show the direction of the flow, so that we know which way the stream is moving. And for this situation, the cold fluid can be actually modeled as something having a large specific heat capacity. Similar to this situation where Cp cold goes to infinity. Okay.